Some black holes weigh no more than a few dozen stars. Others hold the mass of billions, anchoring entire galaxies in their grip. And then there are types that exist only in equations, objects so strange they blur the line between science and speculation. Today, we're going to work through all 5 categories of black holes, from the smallest stellar remnants to the most extreme theoretical possibilities the universe might allow. But before we get into the hierarchy, we need to understand what a black hole actually is. At its core, a black hole is a region where gravity has become so intense that nothing can escape it. Not light, not matter, not even information itself. Picture taking the entire mass of our sun and compressing it down into a sphere just a few kilometers across. The gravitational pull would be so extreme that it warps the fabric of space-time around it, creating what is essentially a one-way trapdoor in the universe. This boundary is called the event horizon. Once you cross it, there's no coming back. Everything that passes through, whether it's a particle, a photon, or a planet, becomes part of the black hole permanently. Now, despite their reputation, black holes aren't cosmic vacuum cleaners roaming through space, devouring everything in sight. If our sun suddenly became a black hole right now, Earth would continue orbiting at the same distance, completely unaffected. The gravitational influence wouldn't change. What makes black holes terrifying isn't that they hunt, it's that they represent physics pushed to its absolute limit. When massive stars collapse, when matter accumulates beyond certain thresholds, or when the early universe behaved in ways we're still trying to decode, black holes emerge as the inevitable result. If you enjoy calm, careful explorations of ideas like this, you might want to like the video and subscribe. It helps the channel continue moving forward. Here's what makes this topic genuinely strange. Not all black holes follow the same rules. Some form from the death of stars only slightly heavier than our sun. Others grow into monsters containing the mass of entire galaxy clusters. And then, there are black holes that have never been observed at all. Objects predicted by mathematics, but never confirmed by telescopes. They live in the space between what we know and what we suspect might be true. That's where our journey begins. Over the next several chapters, we'll climb through the full spectrum of black holes, from stellar corpses left behind by supernovae to quantum-scale enigmas smaller than atoms. Some of these objects are well understood. Others remain mysteries that challenge the foundations of modern physics. This is the complete hierarchy of the universe's strangest and most powerful phenomena. The journey starts now. Chapter 1: Stellar Black Holes. The story of black holes begins with stars. These are the engines that light up galaxies, burning hydrogen in their cores for millions or billions of years. But stars don't last forever. When the most massive ones run out of fuel, they don't fade quietly into the night. They collapse. The core implodes under its own weight, triggering an explosion so violent it can outshine an entire galaxy for weeks. What's left behind after all that chaos can be something extraordinary: a stellar black hole. Not every star gets to have this kind of dramatic ending. Our sun, for example, is far too small. When it dies in about 5 billion years, it will swell into a red giant, shed its outer layers, and leave behind a white dwarf. That's it. No explosion, no black hole. To create a stellar black hole, you need a giant, usually a star at least 20 times more massive than the sun. Once a star like that exhausts its nuclear fuel, there's nothing left to hold it up. Gravity takes over completely, crushing the core down to unimaginable densities. The result is an object that weighs anywhere from 3 to 100 times the mass of the sun, yet occupies a space no larger than a medium-sized city. Think about that for a moment. A black hole might be only 10 or 20 kilometers wide, but it contains the mass of dozens of suns. If you could somehow replace Earth's core with a stellar black hole, our entire planet would be swallowed instantly. The scale is almost impossible to grasp using everyday comparisons. Imagine compressing Mount Everest into the size of a grain of sand, or taking every person on Earth and fitting them all into a space smaller than your thumb. That's the kind of density we're dealing with. So, how do we find something that gives off no light? The answer lies in what happens around them. When a stellar black hole is part of a binary system, paired with a normal star, it can pull gas away from its companion. That gas doesn't fall straight in, it spirals inward first, forming what's called an accretion disk. As the material speeds up and compresses, friction heats it to millions of degrees. At those temperatures, it glows intensely in X-rays. By scanning the sky with X-ray telescopes, astronomers can pick out these telltale signals and trace them back to their source. Gravitational effects offer another detection method. If a visible star appears to be orbiting an unseen companion that's too massive to be anything ordinary like a neutron star, the conclusion becomes clear. And thanks to observatories like LIGO and Virgo, we now have a third approach, listening for gravitational waves. These are ripples in space-time itself, produced when two black holes spiral together and merge. The waves travel across the universe at the speed of light, carrying information about events that happened billions of years ago. Every detection adds another piece to the puzzle. One of the most famous examples is Cygnus X1. Discovered back in the 1960s, it's located about 6,000 light-years away in the constellation Cygnus. At its heart sits a black hole roughly 21 times the mass of the Sun, locked in orbit with a massive blue supergiant star. The system's X-ray emissions were so powerful that scientists couldn't ignore them. Over decades of observation, the evidence piled up until there was no doubt left. Cygnus X1 was a black hole. The discovery was significant enough that it even sparked a friendly wager. Stephen Hawking once bet that Cygnus X1 would turn out not to be a black hole. When the data proved otherwise, he conceded. It was a rare admission from one of the greatest physicists of the 20th century, and it underscored just how much gravity had surprised even the experts. Today, astronomers estimate there could be tens of millions of stellar black holes scattered across the Milky Way. Most of them are dormant, not feeding on nearby stars, so they produce no detectable signals. They drift through the galaxy silently, like cosmic ghosts. Some may remain alone forever. Others will eventually encounter a companion star or merge with another black hole, revealing themselves only in that final moment of collision. Stellar black holes are more than just the remnants of dead stars. They're nature's first demonstration of what happens when matter is pushed beyond every known limit. They show us what gravity can do when nothing is left to resist it. These objects are paradoxes, city-sized regions holding the weight of suns, traps we can only locate by observing their shadows. And they're just the beginning. If this is where the hierarchy starts, the next levels only get stranger. Chapter 2. Intermediate Black Holes. If stellar black holes are the small seeds of the black hole family, and supermassive ones are the giants ruling galaxies, then what lies in between? Logic suggests there should be middleweights, objects heavier than stellar black holes, but nowhere near as monstrous as the supermassive kind. These are what astronomers call intermediate black holes, and they represent one of the most frustrating puzzles in modern astrophysics. On paper, they seem obvious. A stellar black hole might weigh a few dozen suns, while a supermassive black hole can weigh millions or billions. Surely, somewhere in that range, there must be black holes weighing hundreds or thousands of suns. The math doesn't forbid it, the physics seems to allow it, and yet despite decades of searching, intermediate black holes remain some of the hardest objects to confirm. We have candidates, hints, and suspicious signals, but very little that rises to the level of certainty. What makes them so important is not just their size, it's what they could reveal about how black holes evolve. They may be the missing link that explains how small stellar remnants could grow into the behemoths sitting at the centers of galaxies. Without intermediate black holes, it's difficult to understand how the universe built its largest structures. The timeline doesn't quite add up. Supermassive black holes existed surprisingly early in cosmic history, less than 1 billion years after the Big Bang. But stellar black holes shouldn't have had enough time to grow that large through feeding alone. If intermediate black holes exist, they might solve that problem by acting as seeds, giving supermassive black holes a head start. Estimates suggest intermediate black holes should weigh anywhere from a few hundred to perhaps 100,000 solar masses. That's small compared to the titans at galaxy cores, but unimaginably huge compared to their stellar cousins. Imagine compressing the entire mass of a star cluster into something no bigger than a moon. The problem is that finding them is like chasing shadows. They don't have the bright accretion disks of supermassive black holes, and they're not as common as stellar ones. They occupy an awkward middle ground where detection becomes difficult. One place scientists have looked is globular clusters. These are dense spherical collections of stars that orbit galaxies. Some contain hundreds of thousands of stars packed into a relatively small space. Simulations suggest that over time, stars in these clusters could collide and merge, gradually building up a central black hole. If that process happened often enough, intermediate black holes might be hiding in the cores of globular clusters right now. The challenge is proving it. Stars near the center move quickly, which hints at a massive object, but the data is often ambiguous. It's hard to distinguish between a single intermediate black hole and a cluster of smaller objects producing similar effects. Another possibility is dwarf galaxies. These are small galaxies, much tinier than the Milky Way, but large enough to potentially host their own black holes. If intermediate black holes formed in the early universe, some might have ended up at the centers of these dwarf galaxies. Astronomers have found a few candidates this way, but confirming them requires precise measurements of how stars and gas move in the galaxy's core. The signals are faint, and the uncertainties are large. One of the most compelling candidates is HLX-1, located in the galaxy ESO 243-49, about 290 million light-years away. Observations suggest it might weigh around 20,000 solar masses, firmly in the intermediate range. It produces powerful X-ray emissions, consistent with a black hole actively feeding on nearby material. But even here, scientists remain cautious. The evidence is strong, but not definitive. There's always the possibility that what looks like one intermediate black hole could actually be something else entirely, maybe a dense cluster of stellar black holes mimicking the signature of a single larger object. Gravitational wave detectors have opened up another avenue. When two black holes merge, they produce ripples in space-time that carry information about their masses. LIGO and Virgo have detected dozens of these mergers, and some of the resulting black holes fall into the intermediate mass range. This is encouraging, but it also raises new questions. Did these intermediate black holes form from the merger of two smaller ones, or did they exist beforehand? If they're being created through mergers, does that mean the original intermediate black holes are still out there, waiting to be found? It's possible they exist, but are simply too difficult to detect with current technology. It's also possible they're more common than we think, hidden in places we haven't looked carefully enough. Or maybe the universe just doesn't produce them very often, and the gap between stellar and supermassive black holes is more abrupt than we assumed. What's certain is that the search continues. Every new telescope, every gravitational wave detection, every high-resolution image of a galaxy core gives us another chance to catch one. The question isn't just academic. If intermediate black holes don't exist, we need to rethink how supermassive black holes grew so quickly. If they do exist, we need to figure out where they're hiding and why they've been so elusive. Sometimes the most important questions are the ones we haven't answered yet, and intermediate black holes sit right at the center of one of those questions. Chapter 3: Supermassive Black Holes. Now we arrive at the giants. Supermassive black holes are in a different category entirely. We're no longer talking about objects with the mass of a few dozen or even a few thousand suns. These monsters weigh millions, sometimes billions of solar masses. And they're not rare. Nearly every large galaxy in the universe appears to have one sitting at its center, including our own. The Milky Way's supermassive black hole is called Sagittarius A star, or SGR A star for short. It weighs about 4 million times the mass of the Sun and sits roughly 26,000 light-years away from us, at the very heart of our galaxy. For decades, astronomers tracked stars orbiting this invisible object, watching them whip around at incredible speeds. One star, called S2, completes a full orbit in just 16 years, reaching speeds of up to 3% the speed of light at its closest approach. That kind of motion is only possible if there's an enormous concentration of mass at the center, and the only thing that fits the data is a supermassive black hole. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star. It wasn't a photograph in the traditional sense. What we saw was the glowing ring of superheated gas swirling around the black hole's event horizon, backlit by the intense radiation from the accretion disk. The black hole itself remained invisible, a dark void at the center of the light. That image was the result of years of coordination between radio telescopes scattered across the planet, all working together to create a virtual telescope the size of Earth. The resolution required to see something that far away is staggering, like spotting a donut on the surface of the moon. But Sagittarius A star is relatively quiet. It's not actively consuming large amounts of material right now, so it doesn't produce the kind of fireworks we see in other galaxies. For a more dramatic example, we can look at M87 star, the supermassive black hole at the center of the galaxy Messier 87. This one weighs about 6.5 billion solar masses, more than 1,000 times heavier than Sagittarius A star. In 2019, the Event Horizon Telescope captured the first ever image of M87 star, and it became one of the most iconic scientific images of the decade. The photo showed a bright ring of light surrounding a dark center, exactly as predicted by Einstein's theory of general relativity. It was the first time humanity had seen a black hole's shadow. M87 star is also actively feeding. It's pulling in gas and dust from its surroundings, and that material forms a massive accretion disk, spiraling inward. As the disk heats up, it releases enormous amounts of energy. Some of that energy gets funneled into jets, narrow beams of particles and radiation that shoot outward from the black hole's poles at nearly the speed of light. These jets stretch for thousands of light years, far beyond the galaxy itself. When supermassive black holes feed aggressively, they don't just glow, they reshape their entire environment. Supermassive black holes aren't just passive objects sitting at the centers of galaxies. They actively influence how galaxies evolve. When a black hole feeds, the energy it releases can heat up surrounding gas, preventing it from cooling down and forming new stars. In some cases, the jets can blow gas completely out of the galaxy, effectively shutting down star formation for millions of years. This feedback mechanism seems to regulate galaxy growth, keeping galaxies from becoming too large or forming stars too rapidly. When these black holes consume material aggressively, they become some of the brightest objects in the universe. These are called quasars, or more generally, active galactic nuclei. A quasar can outshine its entire host galaxy, producing more light than 1 trillion stars combined. The energy comes from the accretion disk, where gas spirals inward at relativistic speeds, heating up to millions of degrees and radiating across the electromagnetic spectrum. Quasars are so bright that we can see them from billions of light years away, all the way back to when the universe was less than 1 billion years old. That's part of what makes them so puzzling. Here's the problem. Supermassive black holes existed surprisingly early in cosmic history. We've found quasars powered by black holes weighing billions of solar masses, just 700 million years after the Big Bang. That doesn't leave much time for them to grow. If they started as stellar black holes, formed from the collapse of the first massive stars, they would have needed to feed almost continuously to reach those sizes. But there are limits to how fast a black hole can consume matter. There's a point, called the Eddington limit, where the radiation pressure from the infalling material pushes back against gravity, slowing down the feeding process. Even at maximum efficiency, it's hard to explain how some of these early supermassive black holes got so large so quickly. This is where the idea of intermediate black holes becomes relevant again. If supermassive black holes had a head start, If they began as objects already weighing thousands or tens of thousands of solar masses, the timeline starts to make more sense. Maybe they formed through the direct collapse of massive gas clouds in the early universe, skipping the stellar phase entirely. Or maybe they grew through repeated mergers, swallowing other black holes and accumulating mass faster than feeding alone would allow. We don't have a definitive answer yet, but the early existence of supermassive black holes tells us that something unusual happened in the universe's first few 100 million years. Supermassive black holes also play a role in galaxy mergers. When two galaxies collide, their central black holes eventually sink toward the center of the new merged galaxy. Over millions of years, they spiral closer together, losing energy through gravitational radiation. Eventually, they merge into a single, even larger black hole. This process produces some of the most powerful gravitational wave signals in the universe, though they're at frequencies too low for current detectors like LIGO to pick up. Future space-based observatories like LISA are being designed specifically to detect these supermassive black hole mergers. What strikes me about supermassive black holes is the duality. On one hand, they're engines of destruction, tearing apart stars and consuming everything within reach. On the other hand, they're architects of structure, shaping galaxies and regulating the birth of stars. They're both the most violent and the most constructive objects in the universe. Without them, galaxies wouldn't look the way they do. The cosmos would be fundamentally different. And yet, despite their importance, we still don't fully understand where they came from or how they grew so quickly. They remain one of the great mysteries, even as we continue to observe them in ever greater detail. Chapter 4: Primordial Black Holes. Up until now, every black hole we've discussed came from stars or from the slow accumulation of matter over cosmic time. But there's another possibility, one that doesn't require stars at all. Primordial black holes are hypothetical objects that might have formed in the very early universe, not from stellar collapse, but from quantum fluctuations and density variations in the moments after the Big Bang. The idea goes like this. In the first fractions of a second after the universe began, matter wasn't evenly distributed. There were regions where density was slightly higher than average. If those density fluctuations were extreme enough, gravity could have taken over immediately, compressing those regions into black holes before the universe had a chance to smooth things out. These black holes would have formed when the universe was less than a second old, long before the first stars ignited. That's why they're called primordial. They're fossils from the birth of space-time itself. What makes primordial black holes especially interesting is their range. Unlike stellar black holes, which have a fairly predictable mass range based on the stars that create them, primordial black holes could theoretically exist at almost any size. Some might be microscopic, smaller than an atom, with masses comparable to a mountain. Others could be much larger, weighing thousands or even millions of solar masses. It all depends on the conditions in the early universe and how pronounced those density fluctuations were in different regions. One of the most intriguing proposals is that primordial black holes might account for dark matter. Dark matter makes up roughly 85% of all matter in the universe. We can detect its gravitational effects, we see how it bends light and holds galaxies together, but we've never directly observed a dark matter particle. Most physicists assume it's some exotic type of particle that doesn't interact with light or ordinary matter. But what if it's not a particle at all? What if dark matter is actually made up of countless primordial black holes scattered throughout space? It's a tempting idea. Black holes don't emit light, so they'd be invisible. They interact only through gravity, which matches what we observe. And if they formed in the early universe, they'd be distributed throughout space in ways that might align with dark matter's large-scale structure. The math works, at least in principle. But there are constraints. Observations of gravitational lensing have placed limits on how many primordial black holes could exist at certain mass ranges. If there were too many, we'd see more lensing events than we do. So far, the data suggests that primordial black holes, if they exist, can only make up a fraction of dark matter, not all of it. Still, they could be out there. If primordial black holes are small enough, they might be passing through our solar system at any given moment, maybe even through Earth itself, without leaving a trace. Their gravity would be so localized and their size so tiny that we wouldn't notice. A black hole with the mass of a mountain, but the diameter of an atom wouldn't disrupt anything on a human scale. It would just drift through, interacting with almost nothing. There's another reason to take primordial black holes seriously. They might help explain how supermassive black holes grew so quickly in the early universe. We talked earlier about the puzzle of finding billion solar mass black holes less than a billion years after the Big Bang. Stellar black holes shouldn't have had enough time to reach those sizes through feeding alone. But if the universe produced primordial black holes with masses already in the thousands or millions of solar masses, they could have acted as seeds. Those seeds could have started growing immediately, giving supermassive black holes the head start they needed to reach their observed sizes so early in cosmic history. Of course, the challenge is finding them. Primordial black holes don't emit light, and if they're not actively feeding, they don't produce X-rays or other detectable radiation. So scientists have to get creative. One method involves looking for gravitational lensing events. If a primordial black hole passes in front of a distant star, its gravity will briefly magnify the star's light, creating a temporary brightening that can be measured. Surveys like Ogle and Macho have searched for these microlensing events, and while they've found a few candidates, none have been definitively confirmed as primordial black holes. Another approach involves Hawking radiation. According to Stephen Hawking's calculations, black holes aren't completely black. They slowly evaporate over time by emitting particles through a quantum process at the event horizon. For large black holes, this evaporation is negligibly slow. A solar mass black hole would take longer than the current age of the universe to evaporate. But for very small primordial black holes, the ones with masses comparable to asteroids or mountains, evaporation happens much faster. If they're out there and if they're evaporating, they should produce bursts of high-energy particles and gamma rays. Scientists have looked for these signals, but so far, nothing definitive has turned up. That doesn't mean primordial black holes don't exist. It just means they're hard to find, or perhaps they exist in mass ranges we haven't fully explored yet. Each new telescope and each new gravitational wave detector gives us another opportunity to catch one. The possibility remains open, and the implications are significant. If primordial black holes are real, they change the story of black holes fundamentally. They'd no longer be just the final stage of stellar evolution, they'd also be among the first structures the universe ever created. And if that's true, then black holes aren't only about death and collapse, they're also about origins, about the raw, chaotic energy of creation itself.
Chapter 5: Quantum Black Holes.
When most people think of black holes, they picture enormous objects with the mass of stars or galaxies. But what if black holes could also exist at the opposite extreme, at scales so small they make an atom look gigantic? This is the realm of quantum black holes, and it's where our best theories about the universe start to break down. Quantum black holes are entirely hypothetical. They've never been observed, and there's no direct evidence they exist. But the mathematics suggests they're possible, at least in principle. These would be black holes that exist at the Planck scale, the smallest meaningful unit of space, roughly 10 to the negative 35th meters. That's incomprehensibly tiny. A proton, by comparison, is about 10 to the negative 15th meters. A quantum black hole would be 20 orders of magnitude smaller than that. To give some perspective, the difference in size between a quantum black hole and a proton is far greater than the difference between a proton and a galaxy. At this scale, both general relativity and quantum mechanics apply, and that's where the trouble begins. General relativity describes gravity as the curvature of space-time, and it works beautifully for large objects like planets, stars, and black holes. Quantum mechanics, on the other hand, governs the behavior of particles at subatomic scales, and it operates on completely different principles. These two frameworks are incompatible. They use different mathematics, different assumptions, and they predict different outcomes when applied to the same situation. For most of physics, that's fine, because they operate in separate domains. But if you compress matter down to the Planck scale, both sets of rules apply simultaneously, and neither one is fully adequate. This is the territory where physicists hope to find a theory of everything, a unified framework that reconciles gravity with quantum mechanics. Quantum black holes sit right at that intersection. If we could understand how they behave, we'd be much closer to understanding how the universe works at its most fundamental level. But without a complete theory, we're left guessing. One thing we do know, thanks to Stephen Hawking, is that black holes aren't entirely stable. They evaporate. Hawking radiation is a quantum process that occurs at the event horizon, where particle-antiparticle pairs spontaneously appear and one particle escapes while the other falls into the black hole. Over time, this causes the black hole to lose mass. For stellar or supermassive black holes, the rate of evaporation is so slow it's effectively irrelevant. A solar mass black hole would take something like 10 to the 67th years to evaporate completely, far longer than the current age of the universe. But for a quantum black hole, the process is much faster. A black hole with the mass of a small asteroid might evaporate in seconds or less, releasing all its energy in a burst of radiation before vanishing entirely. Could quantum black holes actually form? Some physicists have speculated they might have appeared in the early universe during the brief period after the Big Bang when energy densities were extreme. If conditions were chaotic enough, tiny fluctuations in space-time could have collapsed into microscopic black holes. Most of those would have evaporated almost immediately, but perhaps some survived long enough to influence the universe's evolution in ways we haven't detected yet. Another possibility involves particle accelerators. The Large Hadron Collider, for example, smashes protons together at energies high enough to briefly recreate conditions similar to those in the early universe. Some theories predict that if extra dimensions of space exist, as suggested by string theory, then quantum black holes might form during these collisions. The black holes would be incredibly short-lived, evaporating through Hawking radiation before they could interact with anything else. So far, no such events have been observed, but the possibility hasn't been ruled out entirely. Each time the LHC runs at higher energies, it tests these predictions a little more rigorously. Even if we never detect a quantum black hole directly, the concept itself is valuable. It forces us to confront the limits of our current understanding. General relativity works incredibly well for large-scale phenomena. Quantum mechanics is remarkably successful at predicting the behavior of particles. But we know both theories are incomplete because they can't be reconciled. Somewhere there's a deeper layer of physics we haven't uncovered yet. Quantum black holes are a thought experiment that points us toward that missing piece. They also raise profound questions about the nature of information. One of the biggest puzzles in theoretical physics is the black hole information paradox. According to quantum mechanics, information can never be truly destroyed. But if something falls into a black hole, it crosses the event horizon and is lost forever. Or is it? Hawking radiation seems to carry no information about what fell in, which suggests the information is destroyed. But that violates quantum mechanics. If quantum black holes exist and evaporate quickly, they might offer a way to study this paradox in a more controlled setting, assuming we could ever create or observe one. In some sense, quantum black holes represent the boundary where our equations fail and new physics must emerge. They're not about devouring stars or shaping galaxies. They're about questions that sit at the intersection of space-time, gravity, and the fundamental structure of reality. Whether they exist in nature or only on paper, they remind us that the universe is far stranger than we can currently explain. The answers to some of the deepest questions we have might be hidden in a horizon smaller than a single atom. Chapter 6: Binary and White Holes. We've worked through the 5 main categories of black holes, from stellar remnants to quantum mysteries, but the story doesn't end there.
Beyond these classifications, scientists have proposed other kinds of black holes, some real and confirmed, others purely speculative. Think of this as the bonus round, where observation and imagination meet. One of the most exciting discoveries in recent years has been binary black holes. These are pairs of black holes locked in orbit around each other, circling closer and closer over billions of years. Eventually, they spiral inward and collide, merging into a single, larger black hole. When that happens, the collision releases an enormous amount of energy in the form of gravitational waves, ripples in the fabric of space-time itself that spread outward at the speed of light. In 2015, the LIGO observatory detected gravitational waves for the first time. The signal came from two black holes, each around 30 solar masses, merging together about 1.3 billion light-years away. The collision lasted less than a second, but in that brief moment, it released more energy than all the stars in the observable universe combined. It was one of the most important scientific observations of the century, confirming a prediction Einstein made 100 years earlier and opening up an entirely new way to study the cosmos. Since then, LIGO and its European counterpart, Virgo, have detected dozens of these events. Each one tells us something new about black hole populations, where they form, how often they merge, and what masses they tend to have. Some of the mergers produce black holes that fall into the intermediate mass range, which is helping scientists understand whether that category is real or just a transitional stage. Binary black holes aren't just interesting on their own, they're also tools for probing the universe in ways that weren't possible before gravitational wave astronomy. They're out there right now, spiraling toward each other, warping space-time, and every few weeks, our detectors pick up another one. Then there's a stranger idea: white holes. If black holes are regions of space-time where nothing can escape, white holes are the hypothetical opposite. Nothing can enter a white hole, everything is expelled outward. They're like black holes running in reverse, spewing out matter and energy instead of consuming it.
White holes have never been observed, and most physicists are skeptical they exist in nature. They appear as mathematical solutions to Einstein's equations, but that doesn't mean the universe actually produces them. The equations of general relativity are time reversible, which means if you run the math backward, a black hole becomes a white hole. But just because the math allows it doesn't mean it happens. Physical processes in the real universe tend to move in one direction, from order to disorder, which is why we see black holes, but not their opposites. Still, the concept is intriguing. Some theories suggest that a white hole could be connected to a black hole through a wormhole, a tunnel through space-time linking two distant points in the universe. In this scenario, matter falling into a black hole in one location might be expelled from a white hole somewhere else. It's a seductive idea, especially in science fiction, but there's no evidence for it. Wormholes, if they exist at all, are likely unstable and would collapse before anything could pass through them. And even if they didn't collapse, the physics inside would probably be so extreme that nothing recognizable could survive the journey. White holes also raise questions about thermodynamics. Black holes increase entropy, the measure of disorder in the universe. A white hole would do the opposite, decreasing entropy, which seems to violate the second law of thermodynamics. That doesn't make them impossible, but it does make them deeply unlikely under the conditions we observe. The universe tends toward increasing entropy, not decreasing it. White holes would have to operate under rules we don't see anywhere else. For now, white holes remain a curiosity, a thought experiment that tests the boundaries of general relativity. They remind us that the mathematics of physics can predict things that don't necessarily correspond to reality. Not every solution to an equation represents something that exists in nature. But the fact that we can even conceive of such objects says something about the flexibility and strangeness of space-time itself. These bonus examples show that black holes are more than just astrophysical objects. They're also tools for exploring the limits of theory and observation. From pairs that shake the universe with their collisions to mirror images that may never exist, black holes keep pushing us to stretch both our instruments and our ideas about what's possible.
From the collapse of massive stars to the edge of the quantum realm, black holes reveal a universe far stranger than we typically assume. We've seen how they can be as small as an atom or as massive as billions of suns, shaping galaxies, warping space-time, and testing the very laws of physics. We've climbed through all 5 levels: stellar, intermediate, supermassive, primordial, and quantum. Each one unlocks a different layer of mystery. And beyond them, we've glimpsed the speculative worlds of binaries and white holes, where observation meets imagination. What strikes me most is the range. Black holes aren't just objects of destruction, they're also architects of structure, seeds of creation, and windows into the fundamental nature of reality. They remind us that the universe operates on scales we can barely comprehend, from horizons smaller than a proton to monsters that anchor entire galaxies in place. And despite decades of study, we're still learning. We still don't know how supermassive black holes grew so quickly, whether intermediate black holes are common or rare, if primordial black holes make up dark matter, or what happens at the quantum scale where our theories break down. The universe is not built for easy answers, but it rewards curiosity. Thank you for taking this journey through gravity, space-time, and the edge of what we know. If this exploration made you pause, if it shifted how you see the cosmos even slightly, I'd like to hear about it. Drop a comment below. Which type of black hole surprised you the most? Do you think primordial black holes could be hiding in plain sight? Or are quantum black holes the real frontier? If this video helped you think differently, the best way to support the channel is a like. Subscribe if you want to keep exploring where physics meets the unknown. See you in the next one.